talk, a last lecture on linear regression. And this is also, of course, the last lecture of this year. I hope you enjoyed it. I liked it. I had good moments in this class and also not as good moments in this class, but anyway, thank you very much for choosing my course. I hope you learned. I'm pretty sure that you didn't have an easy time, but and you were challenged by this course, and I kind of like that. But I hope that at least this course have taught you a few things that might be helpful later on in your own career as professionals. Okay, so what we will do today is to, I guess I realize that I need to speak a bit louder. We need to complete that section with a linear regression. And I will begin with essentially, yeah, that's cool. We want it. With first of all the estimation, saying a few things about the estimation of the actual slope. As you see here in this particular formula, we have the estimation of the slope. So beta 1 hat is the estimate, is the point estimate for the slope of the linear regression. And of course, this one, as we mentioned, is the beta sub 0 hat, is the point estimate for the offset, the y-intercept of the linear regression. Now, the matter of the fact is that this slope is not as we would like to have it. For example, it's not going to be like this. So suppose that this is the beta 1 hat, we call it y hat is equal beta 1 hat x plus beta sub 0. This is not the actual only picture because this is only one point estimate. Beta 1 hat is actually the middle of an entire confidence interval within which this value of the true value of the slope belongs to. And actually we will see how to obtain this interval. This is the radius of the interval. The point estimate of beta 1 hat of the slope is in the middle of this. And therefore, what is telling you if the true value of the slope varies anywhere in that line can be like this, or it can be more steep. It can be somewhere in between. Now, of course, as the slope changes, things actually change. And I'm not pretty good here on this line. That should have been a bit closer to actually, this point here is the x bar y hat. It's this point. So then so this is one of the items that we will see today as we talk. We will correlate all of these things not in the concept of the correlation that we're talking here, but in the concept of using teaching a working example to see how I would evaluate all of these things with numbers. Now, we mentioned that before, and I need to mention it one more time. Before you solve a problem, the solution of a problem of linear regression, you must check whether linear regression is relevant or not. For linear regression to be relevant, you must have you must be able to verify that the hypothesis that the correlation coefficient, which is also called linear correlation coefficient, that actually the other Greek letter that we've learned, the rho, is non-zero. So first you run the hypothesis testing with the null hypothesis being that this rho is equal to 0 and the alternative hypothesis being that this rho is not equal to 0. This is a hypothesis testing which is two-sided always because we have 0 versus non-zero. And then you, as we mentioned, you use a statistic which is this R statistic that you see here. So this is the part where we refer about the correlation. And this is the R statistic that we're talking about. Now, observe that the value that this statistic R has t-distribution with n minus 2 degrees of freedom. Don't forget this then. In linear regression, the degrees of freedom for the t-distribution are always n minus 2. So if you can reject the null hypothesis, if the alternative hypothesis is true, is acceptable, then that means that the linear correlation exists between the two random variables, x and y, or between what we would call the explanatory random variable and y, the measurable, the response random variable, and therefore you can proceed with the linear regression. Otherwise, it doesn't make any sense to proceed with the linear regression in the case that you don't have any correlation, in the case that, the null hypothesis is true. Then the slope, the point estimate of the slope is equal to 0, which means that the linear regression line is going to be somewhere flat. It doesn't matter where actually is, but it's flat. It doesn't explain, the linear correlation model does not explain the variability of the data. Now I mentioned that we call y the response variable, and we call x the explanatory variable. Now, in the example that I will show you later, x takes values which it can be, sometimes they will look random, but in the example that I will show you are values that are, it's like if you have a knob and you turn it and you select it. So in this case, that's not at all inconsistent with what we say that the linear regression model talks about two random variables, x and y. X more or less works not as exactly as the cause, but we call it explanatory because the way x changes its values, that change of values for x influences the change of values, or implies, as I would better say, a change of values for y. That's why this is called explanatory and this is called response. But x cannot be considered as a cause, as actually the cause, the mechanical cause for y. So the linear regression shows that two things change values together, but it does not explain why this is happening. If we understand that there is a connection between x and y, x is the response, y is the response variable, and x the explanatory variable, we have to find a way why this is happening. So we don't have an obvious explanation, but at least we have a hint how to look and where to start looking for an explanation. Okay, when in the example that I will show you immediately after that, you see that x takes values like this 14, 15, 16, 17, and so forth until we reach a point. And what you see, y is a random variable which is exactly conditioned by x. And what do I mean? This is exactly what explanation means. That's why we call by x. That's why we call the x to be explanatory, because what you actually see here in the scatter plot, what you will see in the scatter plot when I will show you the scatter plot. Let me show you the scatter plot. So here's my example that I will show you for x and y. In column A, in this Excel file, you see the values of x. In column B, you see the corresponding values for y. And here's my scatter plot. What you see here is that as the values of x change, the values of y change, and what actually, as you see here, the values of a don't seem very random to me. They seem as there's a knob and you're turning the knob, and x takes its values, and y therefore takes also values. What you actually see is not exactly y on its entirety, but you see the conditional random variable y as x takes a value. You don't see the entire variability of y when you do the linear regression model, when you see the scatter plot. You see a variability of y which is tied to how x changes its values. And I would better say, I would better explain that in the way that, or not explain, actually give it a name, is that y is conditioned by x. This is exactly what we say when we observe the values of x, or when we select the values of x, and you see what is the response variable, the value of the response variable y. So let's go to our example again. In this example, as we said, x, the values of x are selected in a certain way. Let's not talk about how they are selected and what they represent. Let's forget that. We have 30 values here for x, and we have also values for the variable y, and the values of the variable y occupy column B. The values of x occupy column A. Now, the values of c are exactly x squared, the squares of the corresponding values of x, and the columns, the values of the column D are the squares of y. And here is the product. X times y. That's what you see in this column. At the bottom, on this line, I form all of those sums. And as you saw in this Excel file, I will try to upload this Excel file so you can have it independently, so you can see the entries as well. We do certain measurements these are measurements that actually, if you look at the formulas in the little set of notes, the very short set of notes, linear regression at a glance, all of those calculations are made here. So, in short, these are the two values I need to calculate the value of R. The value of R is calculated by using these three values, and this is my sample correlation coefficient. Now, using the sample correlation coefficient, I go back and calculate my R here. And the value of this statistic R for this particular example is recorded here on the square that has been highlighted. And as you see, this value is negative 0.8, which is a very high correlation value. So that indicates automatically very strong correlation. That's the sample correlation coefficient, as we call it. And then the value of R, of the statistic as we actually calculated by this formula, is this R capital that I have here, and it's this value that I'm showing to you right now. This is negative 7. And if we look for this value, for negative 7, what is the distribution of R? We said that this one has T distribution with n minus 2 degrees of freedom. We have n to be equal to 30, so we have R has a T distribution with 28 degrees of freedom. If we have a T distribution with 28 degrees of freedom, then if you look at the values, when a value is equal to negative 7, then this negative 7 is exactly, as I would say, off the charts. You can't even find it on the charts here. You can look them up at the, that's distribution. You can try to gain an intuition about this on page 571, about what is the actual p-value. Let me say what that represents. So R has been found to be about negative 7 point something. Negative 7.9. Now R has T with 28 degrees of freedom. So what does that mean? That the PDF to which this one corresponds looks like this. These are this negative 0.709, let's say that it's here. So this area that you see marked with yellow, this is the area that is saying actually how much, that determines actually how much the probability is. And let me explain that. Let me just write the formula. So what I'm interested in is what is the probability that R will take values in absolute value, because we can take positive, we can take negative values. The same picture I can have here, and I can have this black area, and the black area should be equal to the green area here. So this is exactly the event that R takes values greater in absolute value greater than 7.9. This is exactly the p-value for the two-sided interval. So this is a two-sided p-value of the hypothesis testing whether there is linear correlation or not. So since we see that this p-value is very, very small, it's actually so small, 0.002, we understand that we can safely reject the null hypothesis. So the two random variables, so x and y, are linearly correlated, as we call it. Therefore, it's valid to estimate the regression line between the two. If the hypothesis h sub 0, so let's say here, that suppose I'm getting so many windows. So if h sub 0 is accepted, then we say that x and y are independent. Or we say that x and y are not linearly correlated. Either way, either expression means exactly the same thing, but I prefer for you to know this particular. This is the only case where a zero correlation coefficient implies independence. And that is true because we assume that both x and y have normal distribution, although x may take values like what you've seen in this particular example here. Look at the first column. That doesn't look very much like a normal distribution for x, but you can say that x has a normal distribution with very, very big variance. That's why you see the values varying so much between 18 and 82. So there is probabilistically a model that can accommodate the picture for x that you see here. So it seems that I have a little bit of a problem with my window. I seem to be having a problem. that I had. I'm going back here to repeat what I mentioned. The p-value is this, and if you see what is the p-value, it says the absolute, the way we define the event here is that the absolute value of r is greater than 7.09, which means either r is here or either is to the right of this point. Which in any case, this probability, which is the p-value I want, is the sum of the green area and of the black area. Now those two are equal to each other, so you can just find the green area and double that. And they are equal because the statistic R has t distribution, and the t distribution has a PDF which is an even function. So that tells us that since the p-value is very small in this particular example, is equal to 0.002, we infer that h sub 0 is rejected, which actually for this particular example it means that x and y are linearly correlated. And therefore, it's valid to examine whether to solve the linear regression problem. Now, as we mentioned so far, if we look at our Excel file, the correlation coefficient is 0.8, is actually negative 0.8. And if we look at the values of the intercepts, I think we have them here. One is negative 3, so beta 1 hat is negative 3.0. Let's round up the numbers, and beta sub 0 is 577. So those are the point estimates. This is the y-intercept point estimate. And this is the slope point estimate. And now the regression line is y hat. It's always proper to put the hat because that means point estimate. That's what the hat means. Since the slope and the offset are point estimates, therefore the value of the explanatory variable y will also be a point estimate. So that would be negative 3 times x plus 577. So this is the linear regression line. What we know is that the values of y have a normal distribution which has the mean y hat, which you calculated here, namely, let me put it down, negative 3 times x plus 577, and a standard deviation sigma, and an estimate of sigma is the s square that you see in our notes here. Actually, that's the s. So this value, this is the error or noise level, as we call it. This is estimated by S, and actually S is given in this formula here. What is SSE? SSE is the sum of square errors. We actually mention it here. It's calculated by looking how much the actual value of the data at the data point, the y coordinate of the ith point of the scatter plot, is from the point estimate, which is the y I had. So to calculate the y I had, what you do is that you take this formula. So if you go to the x point, so that actually this is the ith point in the scatter plot that corresponds to the ith data point. Then you take yi, which is the true value. You know this value. You subtract the corresponding point estimate. You take the square, and if you sum all of those by exhausting all of your points in the scatter plot, this actually gives you the SSE, the sum of the errors squared. That's a very important quantity. And it's a very important quantity because it tells us how much is the error from the truth, the error of that is created from the interpolation we did, from the regression. If there had been no errors anywhere and no variability, that sigma that we have here should have been equal to 0. So within this particular part, now there are two other quantities that are very important. And this is the total square error, and this is the sum of the residuals of the squares. Let me solve this. Okay, this is the standard terminology. SSR is called the sum of squares due to regression. And the first quantity is called the sum of square errors. And there is another important quantity which you calculate if you do this calculation here. The total error, which is another important quantity, it tells us how much the true values vary from the mean value of y. How much is this? Would say the total variability here. This is y bar, and you sum all of those values as you see. This is called this is called the sum of squares total. There is a formula here which I would call this one here. I would call it Pythagorean theorem formula because it shows that the total error, the square of the length of the hypotenuse, is equal to the sum of the lengths of the square of the lengths of the other two orthogonal sides. Here is the error part, and here is what the model explains. Actually, the SSR, the sum of the squares residual, is exactly the portion of the variability that is completely explained by the linear regression model. That is completely explained, as we say, by this particular regression line. Y hat equals to this. In the scatter plot, as you see it here, if you try to draw the scatter plot, it will be somewhere in between those points. The difference from this straight line, the difference of the points from the straight line, is exactly what creates the error that we call the sum of the square errors, the SSE. And we if we calculate a quantity, as you see here, if you divide SSR by SS total, then you get a quantity which is called coefficient of determination. And this is the so-called R square. We have it in our PDF file. That R square is called coefficient of determination, and the bigger this number is, the more variability is explained, the more the variability is explained by the linear model. If this number is small, then the model does not explain the linear model does not explain the variability we see in the y variable. Now, we did this in this particular example. The last thing that actually two things that I want to do. One is the prediction interval. We've never spoken about the prediction interval. And the other final item is to find the confidence interval for the slope, and actually do it in the example that we are working. It's my windows here. So I had my point estimate for beta 1 hat, which is -3. Let's calculate the confidence interval for beta. So this will be -3.0 minus the margin plus the margin. Now let's see what the margin is. This is T. Now for the margin I have to select a confidence interval. So let's do confidence 95, which means I'll take my alpha to be 0.05, significance 5%. Then this error, because I need a confidence interval, it has to be two-sided. You take the value for the significance divided by 2, and for 28 degrees of freedom, because I have 30 data points, 30 minus 2 will give us 28. Now let's see what this value is going to be. This value is 2.048. And then we multiply this value with this S that we need to calculate times this quantity, so now I want to calculate the margin, and as you see, the margin of error, E, is given by this formula. So now I want to estimate what is here under the square root. Let's look at one calculation. Under the square root we have this sum of squares, and if I do a little bit of expansion inside the parentheses, then that's what I have. X bar squared minus 2 times x bar times x bar plus x bar squared. Now let's pass the sum inside the parentheses. So if you pass the sum inside the parentheses, I'll do it up here. And you have the sum I. You sum all the squares. Then you sum these, and you sum n times x bar, so that will give you n times x bar squared. And now recognize that this is a common factor, factor it out, and now look what you have. This quantity can be written n times x bar. So you have, if you put everything together, you obtain this particular formula, and after that this. Which is easy, and in my case it shows that all of that thing that I have to put under the square root is 13,752. So here finally you have the calculation of the margin of error. So actually you see that we have a quite big margin of error relative to what R is, to what beta 1 is. So we have negative 3.0 minus 0.87 up to 3, negative 3.0 plus 0.87. So the margin of error for beta 1 is actually the beta 1, the slope should be between negative 3.87 and negative 2.13. So this is the estimation for the true value of the slope with confidence 95%. The final thing I want to talk about is the so-called prediction interval. And now we have to see what the prediction interval is. What is the meaning of the prediction interval? As we mentioned, the random variable y, given that x takes a certain value, will have a value with a normal distribution. We mentioned that already. Not this one. Actually, I think I don't need it. I need this. What is the prediction interval? Here is our regression line. What is the regression line? It gives the mean value of y, that actually y bar is the mean value of y when the first random variable x took the value lowercase x. So exactly this guy is the so-called expected mean when x takes this value. Well, if you don't remember this, then let's forget it, because I'm not going to ask you to calculate it ever. I just want you to know this particular concept. So what happens now with the values of y when x takes the value lowercase x? Those will vary around this main line, this main point, and that interval here will have a variation equal to sigma, and we estimated the sigma by estimating the s because of this inequality, and you saw where we did the estimation for s. It's here. Therefore, what I know is that y that comes from the model has a normal distribution with mean y bar. So when x takes the value lowercase x, y has normal distribution with mean equal this one, and standard deviation equal to s. That's an approximation, but truly is this sigma. So the prediction interval wants to find an interval which is going to be bigger than this, and within this interval I will have a very good probability to find the values of y. So the prediction interval let's keep doing tricks here. So this is the prediction interval. This value is what I pointed in this particular value, this one. So let me just draw it. That's the value. And the width is the L. And how do we find the L for the prediction interval? This is going to be, again, the 95% prediction interval because we used the alpha to be 0.05. You use this particular formula here for L. So that's exactly how our L is being found. And of course we need the multiplier quantity here, but don't forget that we also need this S. What does this formula say? The variation for the values of L is slightly bigger than the variation, the likely values for the mean of y. And this is because we have an uncertainty in the slope. And of course that implies an uncertainty in the intercept. We also know that the estimation of the values of y is going to follow a normal distribution with mean, the mean that we have used, that one, and standard deviation, this sigma. However, the values now have to be corrected because this S is, the values of y have to be adjusted because this S is estimated by lowercase s, and the uncertainty in the slope, which makes this straight line, instead of going like this to go like this, creates a little bit of, creates an extra variation here, and this is actually why we take this bigger L, which was given by this particular formula. Well, I guess with this we'll finish, and that actually completes the last talk. Thank you very much, and I will see you in the second exam.